Hey, good afternoon. All right, hopefully you had a good weekend. Just one announcement. The next Tuesday at the beginning of class, we'll be administering the very first quiz. It's not a big deal, right? The quizzes are generally designed to be completed in 25 minutes. And they're always 25 points, so that helps to give you an idea how much time you should be spending on each part of the question. Okay, so generally 25 minutes, 25 points. As I mentioned at the beginning of the semester, it'll be closed book. For the first quiz, you'll be allowed 1 page of notes, front and back. It can be handwritten or typed, or printed, but just 1 sheet of paper, front and back is fine. You should not need to use a calculator. The material to be covered will be the materials of homeworks 1 through 3, essentially the material covering that we covered in lectures 1 through 5. So basically, you'll turn in homework 3 on this Thursday, and you'll get the solutions that night. So you should be able to have ample opportunity to study the material for the quiz in advance. Any questions regarding logistical aspects of the quiz? Yes, question. Constants, yes. The constants that you need, I'll give them to you. Yeah. But I guess you could write them on your cheat sheets. Well, okay. So like charge, right? 1.6 times 10 to the minus 19. Yeah, I'll give you the constants that you need. All right. As I mentioned also at the beginning of the semester, I'll probably try just not proctoring the exam and see how that goes. See if I have any complaints afterwards. Okay? But I'll stay outside in case you have questions during the exam. All right. Were there any questions left over from the lecture last Thursday when I was away? It was on diffusion, carrier diffusion, and also generation and recombination. Any lingering questions? Yes, Ali?
A lot of the diagrams you have.
Energy versus momentum, K-space diagram, energy band diagram. Okay, so these plots, E versus K energy diagrams are, okay, so it's the total energy of the electron as a function of the wave vector, which is essentially proportional to crystal momentum. So that's why I put, it's just h bar times k is essentially the momentum of your electron in the crystal. And remember, the energy of the electron gets affected by the crystal potential. So in direct band gap semiconductor materials, it just turns out that electrons and holes have minimum energy when they're moving in similar directions. So, okay, in the homework that I think you turned in, yes, you turned in last week, most of the electrons are located close to the valence band edge. I mean, most of the holes are located near the valence band edge in a silicon. And most of the electrons are located near the conduction band edge. So same thing here. So electrons primarily are occupying states not too far from the minimum here, and also holes not too far from the minimum here. So fortunately, in a direct band gap semiconductor material, the momentum is also similar. In other words, the average direction, of these electrons and holes is kind of in the same. So electrons and holes, when they meet up, they can recombine. So you have to conserve energy in the recombination process, but you also have to conserve momentum. Turns out in silicon and in germanium, electrons tend to have lowest energy when they're moving in the 100 direction, and this k vector, this minimum, is located actually in the 100 equivalent direction. For holes, it's actually in a different direction, like 110. So basically, you need a lattice vibration to knock the electron to move in the same, have the same momentum vector as a hole in order for them to recombine directly. So it's more likely that an electron first gets trapped by a defect or an impurity atom like gold, and then later the hole comes along and gets trapped at the same time later on. So that's how recombination generally occurs when you have an indirect band gap. So indirect just means that the minimum electron energy and the minimum hole energy is not really at the same momentum. But for this class, you just need to know that for silicon, basically recombination generally occurs through a trap. for a compound semiconductor material that we'll study later for optoelectronic devices, electrons and holes can recombine directly and give off a photon in the visible spectrum. Okay. Yes, question? The question is there any way to change direction? So, okay, so what's illustrated in this slide on the right is that an electron interacts with a phonon, which is a lattice vibration. So, you know, a phonon, an atom can be vibrating in the correct direction and knocking an electron to change its momentum, so then it can match that of a hole, and they can directly recombine. Another way to change an indirect bandgap material into a direct bandgap material is to engineer it on the physical structure on a nanoscale. So if you actually grow a heterostructure, so we grow a thin layer of germanium on top of silicon, and then grow silicon on top of that, and germanium. So basically you grow silicon, germanium, basically you have very, very thin layers of semiconductor. You can actually force you can actually make it more favorable for electrons to move like in a 1-1-0 direction, or holes to move in a 1-0 direction, because you're just basically changing the physical arrangement of the atoms, basically, on a nanoscale. Then the minimum of the electron energy here can match in momentum space the minimum hole energy, and you can get direct recombination. So people have done that. They've done nanoscale engineering of some indirect semiconductor materials to get optoelectronic devices made. So it is done, but it's kind of exotic. It might be easier just to start out with a direct bandgap semiconductor. Yeah. Okay. Did Nuo mention why mid-gap semiconductors are most effective? I forgot. Is that shown somewhere? Yeah, right. Probability is higher. Okay, so I just want to make sure that people understand. So the trap states, so these are defects where electrons like to stay for a while, have energy levels. So the defects have energy levels, allowed energy levels somewhere located within the band gap. And the defects or impurities that are most effective for recombination are located energetically near the middle of the band gap. And the reason for that has to do with, something about trapping easily. So you can easily trap an electron, certainly in a trap state like this. And it'll take some time for electron to get enough energy to escape it, right? So if you have a trap, well, let's see. For example, if you have a donor, so this is a common misconception that, a donor state, in contrast, is up here, right? So if you have like a phosphorus atom inside the silicon, it's going to have an allowed energy level close to the conduction band edge. So electrons can easily escape to the conduction band, right? They have a small ionization energy here. So yeah, an electron coming to a phosphorus atom might get trapped temporarily, but it'll be easily re-emitted, basically escaping from that trap state. So it won't stay in that energy level for very long. But if it's near mid-gap, it'll take a lot longer time because you need more thermal energy to escape this trap. So an electron will tend to stay in a mid-gap trap longer, so the chances of a hole coming by and recombining are greater. Okay. Same thing if you have an acceptor atom, it has an energy level close to the valence band edge, E sub A, let's say, and you can trap a hole very easily, but the hole can be emitted also back into the valence band pretty easily. Okay. So, so the analogy I like to use is like when you were children, did any of you ever get lost from your parents? Okay, so do your parents tell you like how to maximize your chance of being found by them? Is it by you wandering around looking for them all over the place? No, right? You have to stay still somewhere so they can find you, right? So the same thing here. You want an electron, stay there for a long time, and in order for a hole, when it finds you, to recombine. Okay, what's the question? Right, so exactly, that's a great question. So the question is, isn't that bad for dopant? Yes, you're absolutely right. We never want a dopant with an energy level near mid-gap. That's not a good dopant. but that's a good trap. So most of the time, traps are not desirable. They're impurities that can cause recombination or generation, or it makes it easier to generate electron-hole pairs, right? So more easily than going from here to here. That's thermal. That's the normal thermal generation. You leave behind a hole here. You can actually, with the trap state, trap an electron and then over time have an electron go up. So trap states actually are generally not desirable. We'd like to, for higher performance semiconductor devices in general, you don't want a lot of these trap states present. So like things like trace metals, trace amounts of gold or any other metallic contaminant is not desired. But the key thing to remember here is that doping does not affect the recombination and generation lifetime because the dopant levels are not anywhere near mid-gap. And so although dopant concentrations degrade mobility because they're ionized impurities, they're not going to affect the minority carrier lifetime. Okay. Any other questions? Okay. Go on to today's lecture notes, lecture 6. Actually, it's not a very long lecture, so maybe I'll make you guys do some exercises or something. We'll see. Okay, so we've learned about electrons and holes and how they can have action, so drift under the influence of electric field, diffusion under the influence of a concentration gradient, and then they can be created and they can be annihilated by generation and recombination. So today, just to finish the topic of semiconductor fundamentals before we start looking at our first device next time, we just need to finish a couple of more basic pieces of information covering some basics here. So the first one is continuity equations. So a continuity equation, it sounds pretty fancy, but all it is basically conservation of mass or particles. Okay? So it's just a fancy name for keeping track of the number of carriers going in and out of any location in your semiconductor. So let's consider an infinitesimally small slab of semiconductor. So let's say it has some width dx, and the cross-sectional area, okay, I guess I didn't, sorry about that. This cross-sectional area really should be pointing here, right? So this cross-sectional area is A. Let's just say it's a rectangular slab, and its thickness is dx. And the current density of electrons flowing in from the left is J sub n at x, and the current density flowing out of that slab is J sub n also, but at x plus dx. Okay? So to derive the continuity equation, we first just keep track of the particles here. So this term on the left, first of all, what is A dx? Volume, very good. That's all right. So what does that term on the left side of the equation represent? Change in something, that's good. Delta. Okay, change in something. Okay, so this is carrier concentration and electron concentration, but we multiply by the volume. So, right, so it's change in number of electrons within a unit time. So this is inside the volume. Okay, great. Okay, that's correct. Now, well, why would the number of electrons in that slab be changing over time? Well, there's two possible reasons. One is, well, you have more coming in than you have leaving, right? So that's what this first term on the right-hand side represents. It's basically, if there's a difference between the rate at which electrons are entering and the rate at which they're exiting, then there must be some accumulation or depletion of electrons in that volume over time. Does that make sense? So this is the difference between the number of electrons entering and exiting the volume. And current is charge per unit time, so you have to divide out the charge on the electron to get the number of electrons per unit time. And this is current density, so that to get the number of carriers per unit time, you need to multiply by the cross-sectional area, right? This is current per unit area. You have to multiply by the cross-sectional area. Okay, does that make sense? Yes, question. Can I what? That's true. I can take out an A in everything, and we will do that. But this is more like just to keep track of the. If you think of it as conserving electrons, that's how we derive the continuity equation. You're absolutely right. Okay. So what else can happen? Well, so this current density can be due to drift. It can be due to diffusion. It doesn't matter. Okay. It's just the rate at which electrons are entering, no matter what the driving force is. As long as there's a difference between the rate at which they enter and the rate at which they exit, you're going to have a change in the number of electrons in that volume over time. Finally, when the electrons enter, they can, what does this last term represent? Lifetime. Recombination, that's right. So they actually can die or be annihilated due to recombination. So this is the number of electrons annihilated within the volume. So continuity equation, not too scary, right? I hope. It's a differential equation, but hopefully, so there's something that's changing with distance. There's something that's changing with time, so it's a partial differential equation. Okay, so this is just basic, I guess, calculus or math. The current density at x plus dx, you can just say it's equal to the current at x plus the derivative of the current as a function of x times dx. Okay, so this is basically this is the derivative times that infinitesimally small distance. You're just basically approximating this current as a function of x as a linear function. Okay, and if dx is really small, then this is a pretty good approximation. Okay, so if we plug this equation, so rather on the previous slide, for Jn at x plus dx, we just substitute, these two terms in. We'll find then and we divide out a and dx, right? Then we get this more simplified, the simpler expression for the continuity equation. Okay, so the rate of change in the electron density is going to depend on the rate at which the current density is changing over distance. So the change as a function of distance of the current density. And then you have to also take into account net recombination. Okay? All right, so we have a simple set of equations then. So these are the continuity equations for electrons and holes. Now, sometimes we can shine light. So for optoelectronic devices, we shine light on a semiconductor. So to be more generic, we should also include the case of generation of electron and holes by light. So that's what G sub L is. Okay? So this is G sub L is the rate at which these are electrons. Remember, electrons and holes are generated in pairs. Due to irradiation. Let's just call it irradiation. Oops. Okay? So you can basically do the same thing for holes as for electrons, but basically it's just conservation of the number of electrons and holes. Okay? So those are the general continuity equations. So for semiconductor devices, it turns out, well, even that is a little bit too complicated to solve in a general case. So let's look at some special cases. A common special case that's used for a p-n junction diode and for a BJT, bipolar junction transistor, is a minority carrier diffusion equation. Basically, it's a continuity equation, except we only care about minority carriers, and I'll explain why. And there's also another simplifying assumption that the electric field is small. Okay, so there's two. So if we only want to keep track of minority carriers, and let's not worry about the majority carriers, keeping track of the flow of majority carriers and the flow and the concentration of majority carriers. For certain types of devices, it's sufficient to only keep track of the concentration of minority carriers. Then we can actually simplify the continuity equation because the concentration of carriers is small, orders of magnitude smaller than the majority carrier concentration. And so the carrier concentration is small, and if the electric field is small, then basically the drift terms is negligible compared to the diffusion term. Right, so only under these special conditions, if we only care about minority carrier concentrations so that the concentration is small and the electric field is small, then the drift term is negligible compared to the diffusion term. Right, so bottom line is, current due to drift is negligible compared to current due to diffusion. And for that reason, these are called the minority carrier diffusion equations. Okay? So another thing that we assume is that the majority carrier concentrations are constant with distance. In other words, the dopant concentration is not changing with distance. And low-level injection conditions prevail. Okay, so first of all, let's remind, what does it mean to have low-level injections conditions? A majority carrier, so the definition of low-level injection is that the majority carrier concentration doesn't change much. Only the minority carrier concentration changes significantly. And the reason for that is because the minority carrier concentration normally is really so small that a small perturbation can make a big difference. Majority carrier concentration is huge, typically, much larger than minority carrier concentration. So it's harder to disturb that. Okay, so just in bold, these are the simplifying assumptions. Okay, so let's derive the minority carrier equation, diffusion equation, making those simplifying assumptions. Okay, so we start with the continuity equation for electrons. So it's just the same as the slide with the box equations. So one thing to remind you is that N is equal to the equilibrium concentration plus the excess concentration. Now, the excess concentration can be negative. Okay, it's just all we're saying is that we always like to keep track of the carrier concentration relative to the equilibrium, thermal equilibrium value. Okay, so if we want to take the derivative of n, that's essentially equal to the derivative of delta n, right? Because the derivative of this constant is 0. Does that make sense? So it turns out that for the minority carrier diffusion equation, it's just an equation for the excess carrier concentration. And this equation is only valid for a p-type material, right? Because we're talking about electron concentration, and electrons are only minority carriers in p-type material. Okay, so this is for p-type material. Okay, so plugging in, let's see, where, I think I must have done something on the previous, so I basically used the equations on the previous slide. I must have done that, because, right, okay. So if we assume that the current is really just only going to be diffusion current rather than drift and diffusion, then we just substitute only the diffusion current term here in the square brackets. Okay? So assuming then that, okay, this is a little tricky question. Why why did I have to make this simplifying assumption? Okay, look at this equation. Why did I have to make this simplifying assumption that essentially we have doping that's constant as a function of distance? Okay, looking at this equation. Yes, John. Derivative of n naught is 0. Well, that's true, but I'm taking the derivative. Yes, you're right. So derivative of n naught is 0. That's absolutely right. There's another reason that's true. But in order to go from the second line to this third line here, n naught has to be constant with distance. So dn naught dx is 0. But something else also depends on doping. What else? That's right, the diffusion constant, right? So the diffusion constant, did he teach you the rhyme? D over mu is kt over q. He didn't, okay, so that's the Einstein. He didn't give that rhyme to you? He derived it in class, right? Right, so that's an easy way to remember. There's a Einstein relationship between the characteristic constant for drift and the characteristic constant for diffusion, and they're related, right? Hopefully, qualitatively, it makes sense. If an electron moves with higher mobility, then it should diffuse faster, right? So there's a relationship between d and mu. So d over mu is kt over q. That's really easy, hopefully, to remember. Okay, so d, that's right, depends on mobility, and mobility can be affected by the dopant concentration, right? So if the dopant concentration is changing with distance, then d, the diffusion constant, will change with distance. But we'd like to pull that d out of this derivative and put it out here. So that's another reason why we had to make that simplifying assumption. Okay? All right. So I think I must box this, but okay. So that's the minority carrier diffusion equation right here. The rate of change of the excess minority carrier concentration is going to be dependent on the second derivative with respect to the distance. And it also will depend on the rate at which you're losing them due to recombination or generation, or gaining them due to generation. Okay? So we do want to keep track of carriers, both N and P, electrons and hole concentrations, and the fact of whether they're minority carriers or majority carriers. So we do that with a subscript. Right? So the subscript P means that it's the P-type material, and the subscript N means that we're talking about an N-type material. So P sub N means hole concentration in N-type material. So that's the minority carrier concentration in N-type material. And N sub P is just opposite, electron concentration in P-type material. So that's the designation for minority carrier concentration in N-type, P-type material. Shoot, I have a typo here, sorry. This is P-type. Okay. So to be explicit then, we write two equations for electron concentration in P-type material and hole concentration in N-type material. I think the subscripts are correct. Okay, so these are the minority carrier diffusion equations, which are actually just specialized cases of the continuity equations. Okay? All right, so we can use these equations. Actually, when you later on in the class, when you design your transistors, basically the computer program keeps track of making sure that these equations are always satisfied. But qualitatively, you should just understand what they're all about. Okay. Okay. So fortunately, to understand how semiconductor devices work in different regions, we can make simplifying assumptions to come up with simple equations to describe how current flows in a transistor, for example. So let's look at some very special cases that are actually commonly encountered. Steady state. So the definition of steady state means that nothing is changing over time. I mean, no macroscopic quantity is changing over time. So even though at all times you have generation and recombination of electrons and holes, on average, the carrier concentration or the excess minority carrier concentration might not be changing with time. And that's what we call a steady state condition. Okay, so the definition of steady state is that nothing, no concentrations of carriers are changing over time. Okay? No diffusion current. Okay, that's easier to understand. Just that middle term in the first term on the right in the minority carrier diffusion equation is 0. No recombination generation. That is sometimes the case. Just curious. I mean, why do you think perhaps that there's no? There might be a situation where there might be no recombination. So let's say in a semiconductor, somehow, because of thermal energy, you're generating electron hole pairs, but you have no recombination occurring. How can that possibly be the case? Can you think of just qualitatively why that could be the case? If somebody's like generating electron hole pairs, but you never see any of them recombine. That's right. You collect them. That's right. So basically, in principle, in reality, like you apply an electric field. Right? Electric field. Once electron hole pair is generated, you have an electric field. Electron wants to go this way. Hole goes that way. They never see each other again. They never have a chance to recombine. That's right. So that's what happens at a junction, like a p-n junction. Okay. Oftentimes, most of the times, integrated circuits, we don't operate them with light shining on them, so the generation rate is 0. Of course, for optoelectronic devices, they're not designed for that, but for most integrated circuit devices, we have GL equals 0. Okay, so let's do a simple example of how we can use the minority carrier diffusion equation to solve for the carrier concentration inside a piece of semiconductor. And this is a very simple example where you shine light on the surface of a silicon wafer. And because of that light, the photon energy is absorbed by an electron, and it just goes up to the conduction band. So now you generate electron hole pair at the surface. And let's assume that none of the light gets absorbed beneath the surface. So we only generate extra electron hole pairs at the surface. So at x equals 0, that's at the surface, we have some excess minority carrier concentration. And let's just name that delta p sub n naught. Okay, that's just some number, some level of excess carrier concentration. And let's just assume that the light is shining continuously on the surface, and so therefore the system is in steady state. Okay, it reaches some steady state. Some excess carriers at the surface, and carriers will diffuse and die out due to recombination because they're minority carriers, and they'll meet some majority carriers and die out as they diffuse. And so over time, they're going to establish some steady profile, concentration profile versus depth. Okay, so let's solve this. Let's see, remind ourselves the minority carrier diffusion equation. So I'm just going to remind you here. So this is n-type samples, so we care about the excess hole, minority carrier hole concentration. So I'm just repeating the minority carrier diffusion equation here. Okay, that's the same minority carrier diffusion equation. Okay, so this is at steady state. So we can set this equal to 0, right? This rate of change versus time is 0. So we say 0. Rate of change in the excess minority carrier concentration with time. And inside the semiconductor, GL is 0. Okay, so let's just write that. Okay, so GL 0. So this is basically, this is your diffusion equation for this particular case inside the silicon beneath the surface. Okay, so now we have this term. We can move this term here to the right. So, and then divide both sides by d sub p. So we have the second derivative of the excess minority carrier concentration equal to delta, the excess carrier concentration itself divided by dp tau p. So this is equal to, we'll just define this to be L sub p squared. Okay, so L sub p is the whole diffusion length. It's just defined to be the whole diffusion length. So what this is actually the average. You can think of it as the average distance the hole diffuses before it is annihilated due to recombination. Right? So remember, this is an N-type semiconductor sample. So there are many, many electrons. And a hole is a minority carrier. So you have minority carriers diffusing, and the chances are they're going to come across a majority carrier. And when they do, they'll recombine and die out. Okay, so that's basically the definition of the diffusion length. It's just the average distance. It diffuses before, the minority carrier diffuses before dying out. Okay, so from calculus or math or pre-calculus, what kind of a function is defined to be proportional to its own derivative? Exponential, right? So an exponential function is just defined to be like a function where its derivative is proportional to itself. Okay, so if you see this equation here, you're saying the second derivative. If you take a derivative of the derivative, it's still proportional to itself. So now it's also an exponential function, but it can be an exponentially increasing function or an exponentially decreasing function. Okay, so the general solution to this equation is some kind of exponential, right? It's either dying out with distance or increasing with distance. Both of these exponential functions can satisfy that differential equation. There was a question?
I was just going to ask, so this depth into the material, but rather along the material?
Okay, so the question is in which direction is the diffusion length defined? It's actually in all directions. Actually, that's a good question because the mobility is different in different directions, right, because of the crystalline structure. So to be precise, the diffusion constant is different in each crystalline direction. But for this simple purpose, we're talking about the diffusion length in the direction of the diffusion, which is in the concentration gradient direction, like the direction where the concentration is changing. That's the direction that the carriers will be diffusing. Okay, so the general solution can either be an exponentially decaying function or an exponentially growing function. And the way to solve that is that we need two. So there are two unknown, these constants here. So you need two boundary conditions to solve for this profile, this excess carrier profile. So two boundary conditions are that we know, in reality, physically, it makes sense that the holes will die out if you go far deep enough into the semiconductor, far enough away from the surface. So at x is infinity, we know that this function has to go to 0. So that's the first boundary condition. And that tells us that b has to be 0, right? Because if b weren't 0, then x being infinity, the excess carrier concentration will go to infinity. So now if b equals 0, then we know that we just have to solve for a. And remember, we just defined at the surface the excess carrier concentration to be this. So we know that a, well, if you plug in x is 0 right here, you get 1. The exponential of 0 is 1. So at x equals 0, the function has to equal delta p n naught by definition. So the solution is just going to be this term where a is equal to delta p n naught. And so this is the solution for this problem. So it's just an exponentially decaying function, and reaching a maximum at the surface at delta p n naught. What is the okay? So at x equals LP. Okay. So if you go one diffusion length into the semiconductor, what will be the value? What is 1 over e? 1 over 3, roughly. Okay, so about a little over 30%. So we're talking about something around here, right? So basically, on average, most of the carriers die out within a diffusion length. It does take a few diffusion lengths, like 5. Oops, sorry. This is exactly. This is normal. This distance is normalized to LP. Okay, so within a few diffusion lengths, the majority carrier, the excess minority carrier concentration dies out. All right, so this is actually exactly what happens in a solar cell. You generate light, and the carriers do die out. Okay, actually a LED, light-emitting diode. You have carriers die out and due to recombination, and when they recombine, they generate light. Okay, so basically, you would like to make this diffusion length as long as possible if you want to have large volume of semiconductor generating light. Okay, so just out of curiosity, how can you adjust the diffusion length? Sometimes you want a short diffusion length, like for a bipolar junction transistor. No, you never want it. Most of the time, you want a long diffusion length. You don't want the minority carriers to die out too quickly. So how would you dope the semiconductor to get a long diffusion length? If you had a choice. Lightly, right? Because you want to maximize the diffusion coefficient. Does doping affect tau sub p, the minority carrier lifetime? Huh? It'll increase? Okay, what did I say at the beginning of class? Do dopants affect minority carrier lifetime? No, they shouldn't, right? Because it's only the impurities with the trapped energy levels near mid-gap. Okay? So excess dopants, extra dopants do degrade, because they're ionized, they degrade mobility and therefore diffusion constant, but they actually don't affect the minority carrier lifetime. You can introduce other things like trace amounts of metal or introduce defects into your semiconductor, crystalline defects, to degrade tau if you wanted to make the diffusion length short for some reason. Okay, I already said that earlier. So let's do a simple example of calculating the minority carrier diffusion length. Okay, so it's always good to know the sort of the order of magnitude of things. So remember, in a previous lecture, we talked about a typical mean free path. So typical distance that an electron or a hole will travel before it gets scattered by the lattice vibration or by an ion, a Coulombic force. What was a mean free path? Do you remember? Just order of magnitude. Tens of nanometers. Very good. So let's see how long a diffusion length is. So let's say a typical doping concentration level is 10 to the 16 per centimeter cubed. So what would be the procedure for estimating, or just roughly calculating the diffusion length? What's the first step? Huh? Write the equation down. Oh, great. That's good. Okay, so D. Okay, so first of all, this is n-type doped, right? N sub D. So we care about the minority carrier diffusion length. It's the square root. Oh, wait a minute. Of course, that's the hard. Okay, the minority carrier diffusion length is square root of dp tau p. Okay, so we already have tau p. So what do we need? We need d sub p. So how do we find d sub p? Einstein relation. D over mu is kt over q. Great. So remember that nice plot in a previous lecture where we had mobility of electrons and holes as a function of Na plus Nd? And for holes, it's lower, something like this. Remember, it flattens out due to screening, and for electrons, it's higher. Okay, so it turns out that 10 to the 16 is something in the region where it's starting to fall off. So it starts out at about close to 500 or slightly below 500, drops down to about 50 or so. Okay, so for 10 to the 16, if you go back, it's still relatively low, so it's not falling down too much. Turns out that for Nd plus Na equals 10 to the 16, the hole mobility is about 450 centimeters squared per volt second. Okay? That's holes. All right, so D over mu is equal to Kt over Q. So what is Kt over Q? That's something you should know. Very good. So 0.026 times 450. And usually on a quiz, I'll give you a simpler calculation than this. But order of magnitude, do you know what that is? Is it 1, 10, 100? 10, that's right. So it turns out to be 12 centimeters squared per second for the diffusion coefficient, or diffusivity, another word for that. Okay, 12 centimeters squared per second. So yeah, it's good to know in a typical semiconductor, diffusivity is on the order of 10 centimeters squared per second. If you do a rough calculation and you find your orders of magnitude off from that, you know you've probably done something wrong in your calculations. So L sub p is going to be the square root of 12 times 10 to the minus 6. What's the square root of 12? It's like 3.5, something like that. So it's about 3.5 times 10 to the minus 3 centimeters. Okay, so convenient, remember the very first homeworks, you know, the relationship between a micron. So we talk about semiconductor devices typically in microns or nanometers, depending. So it's nice to express the answer in terms of microns. So it's tens of microns. Okay, so it's actually pretty long compared to a mean free path. Okay, and actually the diffusion length is pretty long compared to transistor dimensions. Okay, so let me just remind you, in a typical metal oxide semiconductor transistor, you have heavily doped source and drain regions, and the current flowing between these regions is controlled by the voltage that you put on the gate electrode. And does anybody know that in the most advanced transistors today, what is this minimum spacing between the source and drain? In other words, what is the minimum length of this gate electrode? It's about, yeah, it's about 22. Actually, it's about 25 nanometers. Okay, and it turns out that, you know, drawn proportionately, this is not bad. The source and drain regions here have to be shallower than the gate length for this transistor to work properly. So typically, these junction depths, the depth of these heavily doped regions in the surface of a semiconductor silicon wafer, is going to be less than about 10 nanometers. Okay, so the key here is that, you know, you have a p-n junction here, and these regions are, and the body of the transistor is also pretty small. I mean, it's much smaller than a micron. Right? So the diffusion lengths are actually quite long compared to typical semiconductor device regions nowadays. So we'll come back to that. That's why later in this class we'll talk about short base diodes. In other words, there's a special case if these semiconductor regions are very short, much shorter than diffusion length, we actually can't use the minority carrier diffusion equations anymore. Okay. All right. Any questions in general about this example? Okay. Did I like end half an hour early? No, okay, I didn't. There's a little bit more. Well, I'll end early though. So this is a summary for the continuity equation part. Okay, so remember, it's just based on conservation of carriers, and then it just happens to be simpler to only worry about minority carriers. And so for the special case of minority carriers, we can sort of overlook the drift current due to drift, because the concentration of carriers is small. And usually the electric field strength is relatively small in, let's say, in these, typically in the heavily doped regions of a semiconductor. Okay, so the key thing to remember from the previous couple of lectures is that drift current is proportional to the concentration of carriers, but diffusion current is proportional to the gradient, the concentration gradient of carriers. So diffusion current can actually be significant even if the carrier concentration is small. Okay, and that's the case for minority carriers. And so minority carrier diffusion equations are just a special case of the continuity equation. Okay, so a couple of just minor, topics before we can start talking about semiconductor devices. It's the concept of a quasi-Fermi level. So remember, what was the purpose of a Fermi level, or keeping track of the Fermi level again? Can you remind me? Average energy of an electron. That's true. That's true. But in a semiconductor, the Fermi level is in the band gap, so that's where no electrons can exist. But practically, why do we even keep track of the Fermi level in an energy band diagram in this class? Yeah, we keep track of the concentration of carriers with the Fermi level. So in thermal equilibrium, there's one Fermi level in your system. In other words, one Fermi level can tell you if the concentration of electrons and the concentration of holes. So just to review, in an energy band diagram, let's say we have a Fermi level. As you move the Fermi level closer to the conduction band, you're increasing that, the probability of occupancy of states in the conduction band. So in other words, you're increasing the electron concentration, okay? And as you move the Fermi level down within the band gap, closer to the valence band, you're increasing the probability that a state is empty below the Fermi level, in the valence band. So you're increasing the concentration of holes. So bottom line is, okay, raise the Fermi level close to increase the whole electron concentration. You lower it to increase the hole concentration. Now, in thermal equilibrium, if you have a high concentration of electrons, that means you have a low concentration of holes, right? So one Fermi level can describe both high electron concentration and low hole concentration, or high hole concentration and low electron concentration. But if you're shining light to your semiconductor, you can generate electron-hole pairs, and you can artificially increase the concentration of both electrons and holes. So it's not necessary that electrons have low concentration and holes have high concentration, or vice versa, right? So one Fermi level cannot describe the carrier concentrations if you're not in thermal equilibrium. But it's still nice to be able to keep track of electron and hole concentrations in your semiconductor device, even if you're applying electric field or light. So that's why we introduce the concept of a quasi-Fermi level, like a pseudo-Fermi level, okay? So it's very simple. Instead of E sub f to denote the Fermi level, or to tell us how many electrons and holes there are, or the concentration, we actually have two separate Fermi levels. F, so now it's called F. F sub n for the quasi-Fermi level for electrons, and F sub p, which is the quasi-Fermi level for holes. And if you just compare these equations compared to the thermal equilibrium, the normal Fermi level equations, you can see that basically the purpose of the quasi-Fermi level for electrons is only to tell you the concentration of electrons. And the purpose of the quasi-Fermi level for holes is only to tell you the concentration of holes. Yes, Camille? Where are these located? So that's a good question. We're going to do an example. Okay, so let's do an example. Okay, so I guess the key point to recall is that in thermal equilibrium, you have only one Fermi level, and that's enough to tell you both electron and hole concentrations. If you're not in thermal equilibrium, you need two. One Fermi level to tell you the electron concentration, and one to tell you the hole concentration. So let's do a simple example here. So let's say we have a doped sample. Let's see, it's N-type and doped 10 to the 17 per centimeter cubed. And somehow let's say we shine light on it, and somehow we get excess carrier concentrations 10 to the 14 per centimeter cubed. Remember, so we're generating electron-hole pairs in equal amounts, right? Equal electrons and holes. So the excess carrier concentrations are 10 to the 14 per centimeter cubed. Okay, so first of all, what are P and N? Should be pretty easy. Is that right? Yeah, okay. So what are P and N? Okay, let's find out the equilibrium concentrations first. So P naught and N naught. So in equilibrium, what are these values? So this is an N-type material, right? So which one's easier to figure out first? It's N, very good. So excellent, 10 to the 17 per centimeter cubed. So the equilibrium concentration, as Xue pointed out, is 10 to the third. Okay, but P is equal to the equilibrium value plus excess concentration. And same thing with electron concentration, is the equilibrium value plus the excess concentration. So for holes, which are the minority carriers, yeah, so okay, this is an example. We're not physicists here, we're engineers, so we call this 10 to the 14. Okay, don't keep track of many decimal points, 1 or 2 at the most. Okay, how about for electrons? So it's 10 to the 7, we just call this 10 to the 17 per centimeter cubed. So this is a classic example of low-level injection. The majority carrier concentration is not significantly affected, but the minority carrier concentration is greatly affected. Okay? So what is the NP product? It's 10 to the, yep, very good. 10 to the 31, 31st per centimeter, oops, 6, right. Okay, and notice the key here is that it's much, much greater than Ni squared. Okay, so this is clearly not in an equilibrium condition. So we can't really draw a single Fermi level because this material is not under thermal equilibrium conditions. Okay, so let's find F sub n and F sub p. Let's just draw a single energy band diagram. E sub c, E sub v. And let's just draw E sub I, just for reference, the mid-gap right there. Okay, so F sub n, that's the Fermi level for electrons. That's, the electron concentration wasn't really affected, right, by this excess carrier concentration. So it should be the same as in under thermal equilibrium conditions. Let's just remind you that this is 10 to the 17, this is 10 to the 14. Okay, this is a great example of how, hopefully what you can do quickly on the quiz. Who can tell me where the Fermi level, okay, first of all, is the Fermi level for electrons above or below the intrinsic Fermi level? Above, good. Because, why? That's like really complicated. Okay, no, you're right. So the reason is it's Fn minus EI is positive because n is greater than Ni. Right? In other words, if the carrier concentration is higher than Ni, then you know the Fermi level for that carrier, the Fermi level for electrons has to be higher than E sub I. Yes? Ni is the intrinsic carrier concentration, 10 to the 10. So remember, that's from the first lecture, I hope. Ni is 10 to the 10, and this is in silicon only, and that's only at room temperature, okay? So avoid my trick questions if I ask different temperature. Great. So we know that the Fermi level is above EI. For Fermi level for, quasi-Fermi level for electrons is above EI because n is greater than Ni. Okay, and I'm not necessarily going to draw this to scale, but F sub n is up here somewhere. So what is this distance here? You should be able to blurt it out. What? Oh, 420. All right, good job. 420 milli-electron volts. Why? Somebody want to say why? 7 times 6. I have extra like wafers I wanted to give out here. So does anybody want an extra wafer for answering? Actually, I just noticed I have wafers. OK, so in case you're wondering, these are like memory chips. And some of them are smaller than others. And I think it's because they're more advanced technology. But anyway, who said 420 millivolt electron volts? You did? No, somebody back here did. Oops, somebody back there did. OK, can you pass it back to the fourth person? All right. You've been answering a lot of questions. OK, great. Now, what about the whole Fermi level? First of all, tell me, is it the quasi-Fermi level? Is it below or above EI? Below. Excellent. And how much below? Oh, fantastic. Great. 240. So this is because, OK, I'm just going to make it explicit. So this is 7 times 60 milli-electron volts. This is 4 times 60 milli-electron volts. Fantastic, OK? So essentially, what happened between equilibrium and non-equilibrium? Okay, in equilibrium, you had a single Fermi level up here, right? So equilibrium, I'm going to write this down, E sub F. So in equilibrium, you had a single Fermi level to describe the electron and hole concentrations. And then let's say you shine light on this sample, so you enhance the hole concentration and the electron concentration, but you really don't make, it's a low-level injection, right? So you don't really change the concentration of electrons too much. That's why the Fermi level doesn't change for electrons. It's the quasi-Fermi level that changes for holes. So you need a separate Fermi level to describe the concentration of holes. So basically, you can view it as splitting the Fermi levels for electrons and holes when it's not in equilibrium. So that way, when you're looking at an energy band diagram, you can tell which regions of your semiconductor device are not in equilibrium. It's the ones where the Fermi levels of electrons and holes are not the same. They're split. Okay? Yes, question. Okay, so the question is, yeah, because the equilibrium concentration of electrons is so high that it really, you're not disturbing the concentration. So Fn equals EF. So only if you like shine even more light to generate even more electron hole pairs, more than 10 to the 17 per centimeter cube, then you start to see the Fermi level for electrons going up, splitting, right? So you'll see the splitting even more as you. So you think of it as the Fermi level splitting more and more as you increase. Well, actually, only the minority carrier Fermi level change. And eventually, when you go to high-level injection, both electron and hole concentrations will change. So both the quasi-Fermi levels will change. Okay? Yes, question?
Sorry, maybe some question, but physically, what does not being...
So the question is, physically, what does it mean to not be at thermal equilibrium? Okay, who wants to answer that question? I have more souvenirs. So I have this Frisbee. When I visited Global Foundries, they actually wanted to get rid of stuff. So anyway, I don't know if any of you take notes, but there's a nice leather-bound notebook here. I don't use this anymore. It's pretty nice, actually, gold. Anyway, so who would like to give me a correct answer as to, okay, what does it mean when a semiconductor is not in thermal equilibrium? Like in this case here. You already have a wafer. No, just, okay, please, go ahead.
You can't say that the macroscopic variables are.
Okay, so Ali was saying, yeah, maybe the temperature is different in different parts. That's a good example of a system that's not in thermal equilibrium. That, yeah, the temperature is not the same everywhere. Here, though, okay, in this particular example, I'm not saying that there's a difference in temperature. I think even a more basic, all right, that's good, but not for the leather. Okay. Oh, does somebody else want to give a shot? Great, NP does not equal Ni squared. That's actually correct. No, so basically, thermal equilibrium means that your whole electron and hole concentrations are just determined by thermal energy, right? So depending on how much thermal energy there is in the system, depending on the temperature, you're going to have some, on average, some number of electrons and holes, some concentration of electrons and holes, right? That's what thermal equilibrium means, that electrons and holes only exist because of thermal energy. And if you dope it, yes, you'll tend to favor electrons more than holes, like if for n-type doping. But now this is not in thermal equilibrium because the concentration of electrons and holes is not only dictated by thermal generation and recombination. It's something external. So either applying electric field to inject carriers or shining light to add more electrons and holes. Does that make sense? So equilibrium actually is always implying thermal equilibrium. You can think of it as like due to the natural heat, vibrational energy that you generate electrons and holes in your semiconductor. So in reality, okay, so the question is what happens over time? Yeah, so you're always constantly generating and having recombination occurring, but just on average, you always have like some, n concentration of electrons and Ni squared over P and Ni squared over N concentration of holes, right? So on a microscopic scale, yes, locally you're always going to have some changing electron and hole concentration, but overall on a macroscopic scale, you have a simple equation for N and P. The product has to equal Ni squared, which is a function of the temperature. Okay, so the final thing before we can start to dive into your first semiconductor device is Poisson's equation. Very simple. To keep track of electric field, right? So electric field affects the drift current and so on, we actually have to remember that electric field can vary from one position of your semiconductor device to another if there's charge in your semiconductor device. So from, where is it? Hopefully from maybe high school physics, just in general, if you have, okay, so electric field lines, you have electric field, right? So let's say, very simple, you have electric field lines that go from, let's say this is a simple parallel plate capacitor here. Okay. So electric field lines originate on positive charges and they terminate on negative charges like this, right? So the electric field strength basically is determined by the number of electric field lines per unit area. Now, all Poisson's equation says is that if there's a change in the electric field, if you just look at this bottom equation here, if the electric field is changing with distance, that means you must have some charge somewhere in your semiconductor. So in this case, if for some reason you have like a negative charge here, right, then the electric field strength is changing. Like it's higher here at the top where there's more electric field lines. And somehow you have charge somewhere in your semiconductor or in your device, electric field strength is going to change. Like going from here up here to down there is decreasing, right? That's all that Poisson's equation says. Is that basically if electric field strength is changing, that means you must have some charge in your semiconductor. And there's this this ratio here, the permittivity, E sub s. So I think I've now forgotten, because different textbooks use different values of E sub f. So the relative permittivity of silicon, I think in this class we're going to use, maybe my pen's not working. I'll just say it's roughly 12, but it's something like 11.8 or 11.9. I'll double check next time for the textbook. So it's roughly 12 for silicon. And remember the permittivity of free space is 8.85 times 10 to the minus 14 farads per centimeter. The relative permittivity, as I just mentioned now, or the dielectric constant for silicon dioxide, which is the most common semiconductor insulator material used in our integrated circuits today, is 3.9, but I'll just say it's roughly 4. Okay, so the key here is to know the ratio between the permittivity of silicon to silicon dioxide is 3. So that's something we'll use later on in this class. So we use very coarse numbers here. So just remember it's roughly 12, roughly 4, 12 for silicon, roughly 4 for silicon dioxide. Okay, so let me see. Oh, okay. So what is the relationship between electric field strength? Okay, so this is one equation you should know. Okay. What is another? Okay, so we're going to say electrostatic variables. So there's electric field, which is a function of x. We have charge density, which can be a function of distance as well. And the final one is voltage, or electrostatic potential. I have to apologize. In the previous lecture, sometimes in different textbooks we call that phi or phi, the Greek letter phi. But in Perret, we'll just follow the terminology in Perret. We use capital V to determine electrostatic potential. Okay, so Poisson's equation is nice because it allows us to find, let's say, the electric field distribution in a semiconductor device if we know the charge density distribution. And once we have the electric field distribution, we can easily get the voltage distribution. In other words, we can see where voltage is dropped in our semiconductor device. Okay? So the electric field, what's the relationship between electric field strength and voltage, or electrostatic potential? It's a derivative, some kind of derivative. Okay, in one dimension, let's call it this. There's a negative sign here, right? Okay, so if the electric field is, if the voltage is dropping, then electric field is positive in that direction. Okay, so if we want to plug this, if we know this relationship between electric field strength and the voltage as a function of distance, we can plug that into this equation here. So we find that the second derivative of the electrostatic potential is related to the charge density in a semiconductor. Okay? So when we start going through the semiconductor devices starting next time, we'll probably, let's say we usually start with charge as a function of distance. From that, we can integrate the function to find electric field as a function of distance. And ultimately, what we're most interested in is the voltage as a function of distance, because that will tell us, like, when we apply voltage to our device, where does the voltage drop? Like, which part of the device is the voltage dropping across? Okay, so that's the big picture. And let's go, okay, so let me finish here saying, okay, so where does charge in a semiconductor come from? When you dope a semiconductor material, you add some, let's say, acceptors, and the acceptors will become ionized. And when they're ionized, they'll have negative charge. But those acceptors don't move around, right? They're just immobile. Same thing with donors. They can actually donate an electron, but they're not going to be moving around. They're not going to be contributing to current flow directly, right? They're fixed in their atomic lattice locations. So we have all kinds of sources of charge in a semiconductor. It can be due to ionized dopants, right? So N sub D is positively charged, and N sub A is negatively charged ions. And then we also have mobile charge in a semiconductor. Those are positively charged holes and negatively charged electrons. Okay? So let's do an example. Suppose a semiconductor is doped with phosphorus. And for some reason, the electrons are diffused away. So you dope it with phosphorus. Each atom donates an electron, but electrons diffuse away. This is actually due to, it could either be due to electric field or due to diffusion, for example. Right? There might be a concentration gradient. Okay. So what is the charge density? Let's say it's 10 to the 15 per centimeter cube. So this is not a tricky question, but the only thing is to think about the sign of the charge density. So what is charge density? It's Q times, so the key is don't forget the Q, right? So Q times N sub D, that's right. So it's 1.6 times 10 to the minus 19 times 10 to the 15 per centimeter cube. So this is 1.6 times 10 to the minus 4 coulombs per centimeter cube. Okay? That's a simple example. So the electric field then in this semiconductor is changing as a function of distance. Okay. And anyway, so we'll go over an example of that starting next time when you look at your very first semiconductor device. Okay? So I guess, let's see, to summarize, this is going to be quite common that the charge density, let's say at a junction, like a p-n junction, is going to be determined by the dopant concentration, okay? Because usually the mobile carriers diffuse away for whatever reason, and the charge density is determined by the the dopant concentration, and that's going to determine electric field versus distance, and that will determine how voltage is dropped across your junction. How are the dopants immobile?
So we say if you put in a phosphorus, for example, the electron is
Okay, so somebody wanted, okay, so the question is, how are the dopant atoms immobile? Where is that? So this is from the, I think it was the second lecture. Let's just go over that. So this is actually a key point. In order for a donor to donate an electron to silicon, it actually has to sit in a lattice site. Okay, because it has to be like forming covalent bonds with 4 nearest neighbors, and then the fifth one is not, the fifth valence electron is not really tightly bound. Right, so, well, I don't know what happened here, sorry. So basically the atom has to reside on a silicon lattice site. And when you fabricate a semiconductor device, this is one reason why you shoot donors into this silicon. You have to heat it up to like 1,000 degrees just to get the atoms to rearrange to bond like this. Okay, but see, this donor is bound to the silicon, and it's not going to be moving around. I mean, it'll vibrate among its equilibrium, about its equilibrium position, but it's not going to physically move around and conduct conduct current in your semiconductor. It's the yes, so the extra electron conducts current, right? But I'm just saying in certain regions of a semiconductor device, the carriers, they're free to move around. So they can diffuse away because of concentration gradient, or there can be an electric field that pulls them away. So it's very common in a semiconductor, whenever you have a junction, when you have very steep changes in dopant concentration, that the electrons will leave the vicinity of the donors, and the holes will leave the vicinity of the acceptors. And in those regions, that's where you have some net charge density in the semiconductor, and that's where you have voltage dropped, because there's electric field and so on. Okay, great, thanks. Now, so there's a social hour right outside. Hope to see a lot of you there, and if not, I'll see you Thursday.